Hello everybody, my name is Gustavo Gonçalves. I'm an environmental engineer, master's student in the postgraduation program in renewable energy at the Federal University of Paraíba in Brazil, and supervised by Professor Dr. Rafael Abraão. This work that I will present is a chapter of my dissertation, where I made an economic and environmental assessment of the implementation of a BIPV system, a case study in a tourist complex. This article is entitled Evaluation of Environmental Impacts of a Bio-integrated Photovoltaic System by the Riam method. We know that the biggest contributors to the intensification of global warming are greenhouse gases released into the atmosphere, such as carbon dioxide. These gases come mainly from the burning of fossil fuels to generate heat and electricity. The context of this work is inserted in the use of renewable energy source as an alternative to this problem, meeting the demands and promoting the development of a competitive, reliable, and sustainable energy sector. Within renewable energies, photovoltaic technology is characterized by low carbon emissions, minimal dependence on fossil fuels, and by requiring little maintenance. However, it is necessary to have a well-executed planning for the installation of solar plants to ensure the best use of the economic, environmental, and technical benefits associated with the project. As with any energy source, it can also have potential environmental effects. So environmental impact assessment is an assessment method focused on local environmental aspects in order to explore the likely impacts of a given project. Bio-integrated photovoltaic, the BIPV, is a photovoltaic technology model that transforms solar modules into part of the structure, attributing functionality beyond electrical generation. When compared to the traditional model of installation photovoltaic system, decoupled, the BIPV has some advantages, such as the performance of its components as construction elements, economy with building materials, and the possibility of better use of the efficiency of the modules, due to the greater variability of locations that can be used for installation. Therefore, the objective of this manuscript was to identify the environmental impacts related to the implementation, operation, and deactivation phases of a BIPV and carry out their assessments using the Rapid Impact Assessment Matrix, the Ryan method. Our study object is a proposed BIPV to replace the parking cover at the Serrote do Jatobá tourist complex. The complex is under construction and is a work of the municipal government of Pau dos Ferros, state of Rio Grande do Norte, Brazil. The proposed system has 770 square meters and must meet the demand of 386 kilowatt-hours per day. The listing of the main impacts incident on the three phases of the project was carried out by the control listing method. For the purpose of evaluating these impacts, a matrix of the Ryan type was created. We begin by framing the components to be evaluated into four categories. They are physical-chemical, biological-ecological, social-cultural, and economic-operational. Then begins the process of evaluating the impacts. Each impact was assessed following these criteria. These criteria were divided into two groups. A group are the important criteria for the condition, that individually can change the score obtained. In it we have the importance of the condition and magnitude of change. B group has the criteria that are not individually able to change the score obtained. They are permanence, reversibility, and cumulativeness. Each impact received a score within the scale of each criterion, corresponding to the description of what that score means. These assigned values were then subjected to a series of simple formulas, which determine the scores on a defined basis. For A group, a linear multiplication of the scores attributed to each impact was proposed. For B group, was just the sum within the group. Then, the total A and total B were multiplied and obtained the environmental score, ES, for each of the impacts. The ES values were defined in an alphabetical range, positive and negative. The ES values of each impact represent the disturbance level of the impact, as described in the third column. A differential of this manuscript was the submission of the set of AS values obtained to the statistical tests of Shapiro-Wilk, Levin, and t-test for independent samples to test normality, homogeneity of variance, and the difference between means, respectively. So let's go to results and discussion. This is the matrix filed with the assessments. These are the aspects listed. These are their respective impacts. Note that some aspects cause more than one impact. In total, there were 14 aspects and 22 respective environmental impacts. These are the categories into which the impact has been framed. Here, is the phase where the impact occurs. Waste generation occurs in the three phases, so it was counted 3 times. In the implementation phase, 13 possible changes were accounted for. In the operation there were 10, and in the activation there was only 1, totaling 24. And these are the evaluation cells, where scores are assigned for each criterion, for each impact for A group and B group. These are the calculated AS values, and these are the assigned ranges. The main positive environmental impacts were the generation of scientific tourism and the qualification of the workforce, as well as its hearing, with an AS of 48, the consequent strengthening of local commerce, profitability throughout the project's lifetime, in addition to the green benefits defined between the generation of green energy and the decarbonization of the electricity network, all with an AS of 36. The negative impacts were presented as possible contamination of the soil and water bodies resulting from the generation of solid waste and effluents from the installation phase process with a negative AS of 36, maintenance of equipment in the operation phase, mainly by the use of chemical substance to clean the panel, and in the disposal of parts during the activation, both with negative AS of 42. In addition, the disturbance, scaring, and risk of accidents with the fauna, and the alteration in air quality due to particulate matter must also be considered, all with negative AS of 24. Changes in air quality pose the greatest risk to the local population. According to the range bands classification, most of the impacts listed are significant positive, corresponding to 25% of the total. Next, the minor negative impacts are the most numerous, responsible for 20.8%. Moderately positive impacts comprise at 16.7% of the general, while moderately negative impacts at 12.5%. There was a tie between the slightly positive and the significant negative with 8.3%, and between the slightly positive and negative with 4.2%. There are not impacts considered A positive and negative or N. As we can see, the most impacted category is the economic operational, with 14 impacts. These positive impacts are those related to the acquisition and improvement of labor, technical scientific visitation, financial returns arising from this flow of visitation, and the associated environmental benefits due to the role of photovoltaic energy in mitigation global warming. These negative, on the other hand, are strictly related to risks with the safety of workers, the well-being and quality of life of the surrounding population, and the loss of jobs at the end of the installation. The site's good solar indices also contribute to the better payback when doing NPV analysis. The second most impacted category was physical chemical, with a total of 7 impacts. The particularities of the BIPV make them especially striking in this category, as the constructive mode stands out for the use of a built-up space for the installation. The site's good solar indices also contribute to better payback when doing NPV analysis. The second most impacted category was physical chemical, with a total of 7 impacts. The particularity of the BIPV make them especially striking in this category, as the constructive mode stands out. As there is a semi-arid region, one of the biggest concerns is the limited availability of water resources, and the conflict between solar installation and the use and quality of water results from 2 factors: both the volume captured for cleaning the system that is not replaced, and the use of chemical products and for cleaning the equipment. There is also the possibility of emission of particulate matter due to the transport of equipment and the increase in vehicle traffic in the area. The soil in the region has a stone surface coating with high levels of silt, being highly susceptible to erosive process, and soil particles can easily be carried away by the wind, changing the air quality and impacting the health of those in contact. A positive point of the BIPV is that, as it is integrated into the building, it avoids the economic problem of acquiring land of its installation, and also land use conflicts for agriculture, a very common problem in the installation of solar plants. In addition, BIPV has the innovative effect of design, which reflects even in the evaluation of property. Between categories social-cultural and biological-ecological, the quantifier of impact is much lower when compared to the previous categories, with 2 and 1 respectively. They comprise the actions that interfere with the quality of life, positively or negatively, in the social-cultural and natural environment. They describe disturbance to the nearby community and to faunal and floristic species during the lease phase of the construction site that stop happening when the photovoltaic system comes into operation and the site is deactivated. In addition, it is also considered the professional qualification work to be carried out with the construction employees. With the statistical tests, the normality and the homogeneity of the variance was attested, and that there is a significant difference between the AS values referring to the positive and negative impacts. These results indicate that the AS of the positive impacts are considered on average higher than the negative ones. There is a greater dispersion of AS values for negative impacts when compared to positive. Also, negative values are further away from the mean and positive values closer. Regarding the importance of the condition, it is observed that the positives have a distribution that involves all levels of importance, mainly for areas immediately outside the local condition. The negatives, on the other hand, are divided between importance for local condition and immediately outside them. Among the values assigned to magnitude, both positive and negative impacts cause mainly significant change in the status quo. As for permanence and reversibility, the positive impacts were mostly permanent and irreversible, while the negative ones are mostly temporary and reversible. In both groups, most impacts were presented in a non-cumulative way. Many of these negative impacts can be mitigated, minimized, and/or compensated through appropriate management and monitoring measures, such as land and water management plans, flora and fauna management, among others. So what do we conclude with all this information? In this impact assessment, 14 different aspects and 22 respective environmental impacts were evaluated, mostly significantly positively, encompassing the 4 categories provided in the methodology. In addition, the environmental performance on the enterprise can still be favored if mitigation and/or compensation measures are instituted, as well as adequate monitoring. The positive points were related particularly to economic development, to the improvement of the workforce, and the environmental aspects. The negative ones were associated in particular with the threat to safety of workers, waste generation, and consequence of the insertion of the construction site. In short, BIPV presents itself as a solution to meet the electrical demand in locations that face land use and occupation conflicts, due to its integration with building or structures. This adaptation helps photovoltaic energy not to deviation from sustainability goals, for example, through the preservation of biota and ecosystem service, which will be more affected in the photovoltaic plants were installed on the ground. In addition, this work is a pioneer in the application of this methodology to study the insertion of photovoltaic energy. These are the references that were used, and I hope you enjoyed it. If you want, you can contact us by email. These QR codes will take you to our profiles on ResearchGate. Thanks for the attention.